Okay, so my topic is like basically the Earth's shape. Okay, so the table of contents, I'll first be going over like what spheres are and what they actually are, and I'll next be going over the flat Earth theory and why people thought the Earth was flat, and then I'll go over why the Earth appears as a sphere, and then I'll be going over how gravity affects the shape of Earth, and then about Isaac Newton and his invention of the reflecting telescope, and then Earth's plasticity and gravity's effect on not only Earth but organisms. Okay. It's pretty much general knowledge that Earth is like a sphere, as it was like discovered pretty early on by two philosophers, Aristotle and Pythagoras. The definition of a sphere is a geometrical figure that is perfectly round, three-dimensional, and circular like a ball. So before I go into why the Earth isn't actually a sphere, I'm going to go over what people thought the Earth did look like. In early Egyptian and Mesopotamian thought, the world was portrayed as a disk floating in the ocean. A similar model is found in the Homeric account from the 8th century BC, in which Okeanos, the personified body of water surrounding the circular surface of Earth, is the starter of all life and possibly of all gods. The pyramid texts and coffin texts of ancient Egypt show a similar cosmography. Nun, which was the ocean, encircled MBWT, or dry lands. The Israelites also imagined the earth to be a disk floating on water with an arched firmament above it that separated the earth from the heavens. The sky was a solid dome with the sun, moon, planets, and stars embedded in it. Another philosopher, Thales, also believed in a sort of flat earth. Thales thought that the earth floated in water like a log. It has been argued, though, that Thales actually did believe in a round earth. Anaximander from 550 BC believed that the Earth was a short cylinder with a flat circular top that remained stable because it was the same distance from all things. Anaximenes of Miletus believed that the Earth is flat and rides on air. In the same way, the sun and the moon and the other heavenly bodies, which are all fiery, ride the air because of their flatness. Xenophanes of Colophon, which was in 500 BC, thought that the Earth was flat, with its upper side touching the air and the lower side extending without limit. Belief in a flat Earth continued into the 5th century BC. Anaxagoras, in 450 BC, agreed that the Earth was flat, and his pupil Archelaus believed that the flat Earth was depressed in the middle like a saucer, which means there's a little divot in the middle, to allow for the fact that the sun does not rise and set at the same time for everyone. But it is physically impossible for the Earth to be flat for 5 reasons. First, if the Earth were a flat disk, that means that there's only one possible orientation, that the Sun-Earth-Moon alignment can take place in order to create a circular rather than elliptical shadow, with the Earth's disk perpendicular to the Sun-Moon plane. This means the Sun would need to be at the midnight position relative to the night side of the Earth, and yet lunar eclipses occur at all different times depending on where you are on Earth. The flat Earth cannot explain that. Next, if the Earth were flat, the Sun's rays would always come in at the same angle, meaning that the US, Australia, Italy, and Argentina would all experience the seasons the exact same way. Next, if the Earth were flat, everyone on the night side of Earth would see the same sky, which they do not. And next, Mauna Kea, which is the highest peak in Hawaii and the summit of the Big Island, with nothing but the ocean around it and a few other nearby islands, you should be able to see extremely far away. The island of Kauai has the 7th highest point in the Hawaiian Islands, the peak known as Kawakini. If you were to draw a straight line from Mauna Kea, which has an elevation of 13,796 feet, to Kawakini, which has an elevation of 5,226 feet, it would span a distance of 303 miles. However, you cannot see one from the other, which you would absolutely be able to do if the Earth were flat. But with a curved Earth of its measured radius, the line of sight limit for those two elevations caps out at 233 miles. Only with a curved Earth is one invisible from the other, and this is true for any two mountain peaks with clear line of sights from one to the other. And finally, if the Earth were flat, then someone in New York and someone in Los Angeles would see the sun rise and set at exactly the same time as one another. But in practice, the difference is approximately 3 hours. Not only that, but at every point in between, the sun rises and sets at a different time, something that, something that could not happen if the Earth were flat. Aristotle stated that the Earth was spherical because of the circular shadow that was casted on the moon during a lunar eclipse. A lunar eclipse is basically where the moon moves in an orbit around Earth, and at the same time, Earth orbits the sun. Sometimes Earth moves between the sun and the moon. When this happens, Earth blocks the sunlight that normally is reflected by the moon. This sunlight is what causes the moon to shine. Instead of light hitting the moon's surface, Earth's shadows falls on it. This is an eclipse of the moon, a lunar eclipse. A lunar eclipse can only occur when the moon is full. A lunar eclipse can be seen from Earth at night. And there are two types of lunar eclipses, a total lunar eclipse and a partial lunar eclipse. A total lunar eclipse occurs when the moon and the sun are on exact opposite sides of Earth. Although the moon is in Earth's shadow, some sunlight reaches the moon. The sunlight passes through Earth's atmosphere, which causes Earth's atmosphere to filter out most of the blue light. This makes the moon appear red to people on Earth. A partial lunar eclipse happens when only a part of the moon enters Earth's shadow. In a partial eclipse, Earth's shadow appears very dark on the side of the moon facing Earth. What people see from Earth during a partial lunar eclipse depends on how much the sun, Earth, and moon are lined up. Another reason was that the stars of Egypt were not seen further north, which you should be able to do if the Earth was flat. You could also kind of see boats dip into the horizon as they got further after departure. And finally, an example of eye height supports the fact that Earth is not flat, because the higher you go, you'll be able to see more. Those were all visual examples, but scientifically, the Earth is round because of gravity. A planet's gravity pulls equally from all sides. Gravity pulls from the center to the edges like the spokes of a bicycle wheel. This makes the overall shape of a planet a sphere, which is a three-dimensional circle. Photographs from outer space satellites depict Earth as a perfect round sphere, where in reality it actually isn't. The picture on the right is a simulation of what the Earth actually looks like, which, according to NS Science article, is actually more like a lumpy potato. A satellite orbiting Earth has confirmed that the planet is not the simple square sphere we often imagine it to be. It is in fact more like a lumpy potato. Nearly a year's worth of gravitational measurements from the European Space Agency's gravity field and steady-state ocean circulation explorer have yielded a colorful map portraying the geoid, the shape the Earth's surface would be if it was entirely covered by water and influenced by gravity alone. The result is not a smooth sphere, because mass is not distributed evenly within the Earth's mantle. Different parts of the globe exert a different gravitational pull on the ocean, meaning that sea level is lower than expected in some places, which is represented by the blue patches, and higher than expected in others, the red and yellow patches. The variation in apparent gravitational acceleration at different locations on Earth is caused by two things. First, the Earth is not a perfect sphere. It is slightly flattened at the poles and bulges out near the equator. So points near the equator are farther from the center of mass. The distance between the centers of mass of two objects affects the gravitational force between them. So the force of gravity on an object is smaller at the equator compared to the poles. This effect alone causes the gravitational acceleration to be about 0.18% less at the equator than at the poles. Second, the rotation of the Earth causes an apparent centrifugal force, which points away from the axis of rotation, and this force can reduce the apparent gravitational force, although it doesn't actually affect the attraction between two masses. The centrifugal force points directly opposite the gravitational force at the equator and is zero at the poles. Together, the centrifugal effect and the center of mass distance reduce gravity by about 0.53% at the equator compared to the poles. In this visualization, the vertical scale has been exaggerated by a factor of 7,000. So the pits and crests are 7,000 times shallower or taller, respectively, than depicted here. The visualization shows true sea level liberated from the artifacts of tides and winds. Mission scientist Roger Hagman explains that the influence of winds on the ocean through a simple model. Suppose that you have a bathtub full of water and you place a fan on one side to blow the surface. The water will pile up on the opposite side. Now let's shut the fan off and the water will settle at a new level according to gravity. The new geoid map will be useful for studying ocean circulation, ice dynamics, sea level change, and earthquakes. We want to have a system to describe the actual ocean currents, how all the currents actually are in the absolute sense, because they transport heat and influence climate, Hagman says. When we get more data, we can make the final model more accurate and map the smallest currents. The shape that Earth fits the best is an oblate spheroid, or a sphere that has a squashed top and bottom. The first person to discover that Earth was an oblate spheroid was Isaac Newton. Isaac Newton, who is often called father of modern science, is famous for his discovery about gravity when he was hit by the apple while sitting beneath a tree. He was a student of Cambridge University, and he also created the world's first reflecting telescope. Reflecting telescopes use mirrors to help astronomers see more clearly faraway images in space. A mirror collects light from objects in space, forming the image. This first mirror, which can be very wide, reflects the image onto another mirror. Later, Newton was elected to a fellowship in Trinity College in 1667 after the university reopened. 2 years later, Isaac Barrow, Lucasian professor of mathematics, who had transmitted Newton's analysis to John Collins in London, resigned the chair to devote himself to divinity and recommended Newton to succeed him. The professors exempted Newton from the necessity of tutoring, but imposed the duty of delivering an annual course of lectures. He chose the work he had done in optics as the initial topic. During the following 3 years, which was 1670 to 1672, his lectures developed the Essay of Colors into a form which was later revised to become book one of his series called the Optics. Isaac Newton first proposed that Earth was not perfectly round. Instead, he suggested it was an oblate spheroid, a sphere that is squashed at its poles and swollen at the equator. He was correct, and because of this bulge, the distance from Earth's center to sea level is roughly 21 kilometers or 13 miles greater at the equator than at the poles. Instead of Earth being like a spinning top made of steel, explains geologist Vic Baker at the University of Arizona, it has a bit of plasticity that allows the shape to deform very slightly. The effect will be very similar to spinning a bit of silly putty, though Earth's plasticity is much, much less than that of the silicone plastic clay. Plasticity is the ability of certain solids to form or to change shape permanently when subjected to stress of an intermediate magnitude between those producing temporary deformation or elastic behavior, and thus causing failure of the material or rupture. Plasticity enables a solid under the action of external forces to undergo permanent deformation without rupture. Elasticity, in comparison, enables a solid to return to its original shape after the load is removed. Plastic deformation occurs in many metal-forming processes, such as rolling, pressing, and forging, and in geologic processes such as rock folding and rock flow within the Earth under extreme high pressures. Earth is one of the solids where during orbit it is stretched permanently, which is why it is flat at the poles. Finally, gravity is extremely important not just for convenience but also for our health. We have all experienced the force of gravity. It is what happens when you to you when you jump into the air. Disappointingly, for anyone with ambitions to become Superman, we intend to fall right back to the ground. But what if we could switch gravity off? It is now an established fact that astronauts lose bone mass and muscle strength during stints in space, and their sense of balance changes. An absence of gravity brings other problems as well, as Kevin Fong explains. For reasons not entirely clear, our red blood cell count fails, bringing on a form of space anemia. Wounds also take longer to heal, and the immune system loses strength. Even sleep is disturbed if gravity is absent or weak. So even though being able to fly from place to place sounds pretty cool, we shouldn't take gravity for granted. Thank you.
Okay, thank you so much, Kevin. And let me share